Hello, in today's video we're going to be talking about the ideal gas law. Now the ideal gas law makes some assumptions about our gas that we're dealing with. And so the ideal gas law only works on a very specific subset of all gases. So when can we use the ideal gas? Well, if we have a very small molecule, we can use the ideal gas. So this is good for small things, for small gases, such as H2. H2 is a very small gas. The ideal gas works very well at predicting how this gas is going to move and the units associated with it. So it's very good at small gases. It's also good at high temps, high temperatures. Okay, those are the two cases where the ideal gas law will hold true. Any other time, we're going to have to make some adjustments to the ideal gas, and we'll be doing that on Friday. But for today, we're going to be dealing with this ideal gas. So let's say we're starting with an ideal gas. It's a small molecule of gas. It's at very high temperatures. It's flying around. There's no interactions between the molecules. This is a good thing. We can come up with what's known as the ideal gas. This uses a new constant that we've never seen before, as well as those four different variables that we've dealt with the three named gases. Boyle's law had pressure and volume. Avogadro's law had volume and temperature. And then Charles' law had volume and temperature. And Avogadro's law had volume and moles. So we have pressure, volume, temperature, and moles. Those are the four different variables that we can assign to this ideal gas. And how the equation looks for the ideal gas law is pressure times volume. This comes out of Boyle's law. We know that P1V1 equals P2V2 is equal to the amount of material. Well, this is very similar. If I were to divide both sides by n, I would get V over n. Well, that's similar to Avogadro's law. Times a constant, we don't know what that is yet, and then times temperature. Now, if I divided both sides by temperature, I would get V over T. That is identical to Charles's law. So all three gas laws were used in order to make this ideal gas law. So let's go through and see. So we know that this is pressure, this is volume, this is amount in moles, and this is temperature. And just like with Charles's law, where temperature had to be in kelvins, temperature is going to have to be in kelvins here as well, based on what our gas constant is. So this is called our gas constant. We use capital R for a lot of constants in chemistry. So what is the gas constant? It is 0.0821. So it's just a bunch of numbers together. It will never change. Now the units are strange. The units are liters times atmospheres divided by moles times Kelvin. So that's slightly different than what we've seen before. This has four different units squished into one problem. Now you saw something that had three different units on the last exam, so this is stepping it up even one more notch. So this is the ideal gas law. Now, how do we use this? If we are able to measure any three of the four variables, so P, V, N, or T, any three of those, we can solve for the fourth one. So let's see how we can do this with a problem. Let's say we have a gas, an ideal gas. Let's say we have hydrogen. And we know that the pressure of the system is at 1.0 atmospheres. We know that the volume of the system is at 22.0 liters. We know that the temperature is at 300 Kelvin. These are all things we can measure in a laboratory. We want to find out what the moles are, and from that, I want to know the mass in grams of H2 that are in this apparatus. So the ideal gas law allows us to solve for the moles. To go from moles to mass, we have to know how to go from moles to mass. We already know how to do that. We use the molar mass of hydrogen. So let's plug in our values. Let's solve for this N. I'm going to draw a line here. N is equal to P V over RT We're going to plug in our values, 1.0 atmospheres times 22.0 liters divided by R, which is 0.0821 liters atmospheres per mole Kelvin, times 300.0 Kelvin. Let's see if the units make sense. We're trying to solve for moles here. So atmospheres are going to cancel, liters are going to cancel, kelvins are going to cancel. The moles is in the denominator of a denominator, which in mathematics means that it flips up to the top. So we have the correct units here. If we solve for this, we end up getting 0.89322 moles of H2. Now that's part of the question. The second question was to identify the mass of hydrogen gas that is present. Well, we know how to figure out the molar mass of hydrogen. We look at the periodic table. It is 2.02 grams of hydrogen for 1 mole of hydrogen. If you cancel out the moles, we're left with grams of hydrogen. This ends up giving us a mass of 1.80. I rounded here. I got 3 sig figs and I rounded here. Grams of hydrogen. So you can see that with the ideal gas, we can manipulate it in such a way that we can solve for 1 out of the 4 variables. We use our new gas law, or our new gas constant, with these weird funky units of liters atmospheres per mole Kelvin. Of course, if I was given pressure in torr, we can convert this unit, this constant, into torr by converting the units. We then solve for the moles of hydrogen. And then from there, we're going to multiply by the molar mass, and we're going to find out what the mass is of the hydrogen gas that's present in the system. So what this says is we have 1.80 grams of hydrogen gas present in our system. Now, there's one last thing I want to talk about. This is a simple problem. We're going to be dealing with a lot of these problems tomorrow. We know that this has a constant in it. So I can rearrange this equation to R is equal to PV over NT. This allows us to write out something known as the general gas equation as well. General gas law. So what does that mean? This is very similar to our named gas laws because we had, for Boyle's law, pressure P1, V1 is a constant. In this case, PVNT is a constant. So now we can set up a new equation, P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. This equation here is the general gas law. This allows us to see how any of the variables will change over a given time frame. So if we know the initial pressure, volume, moles, and temperature, and we know the secondary volume, moles, and temperature, we can figure out what the secondary pressure is. So using the ideal gas law, we've done a simple derivation using the constant, the idea of this constant, that we can set up a new way of identifying the 4 different variables. So we're going to be dealing with all of these gas laws tomorrow. On Friday, we'll go to even our last gas law, and then we'll be done with chapter 5. So with that, I want to say have a great night. I will see you all in class tomorrow.